Serving open-source models efficiently at scale is now the primary engineering bottleneck in enterprise AI. A model like Llama 3 70B requires 140 gigabytes of VRAM just to load its static parameter weights. If you try to load that into a standard 80 gigabyte NVIDIA A100, the model physically exceeds the hardware's capacity. Engineers operate inside a strict optimization triangle. Every deployment must balance infrastructure cost against generation speed and raw answer accuracy. Increasing raw compute power is cost prohibitive. Achieving scale requires re-engineering how the system manages GPU memory. While training is a one-time expense, inference costs are incurred on every prompt. This makes memory engineering a central driver of the long-term cost per token for AI products. Modern GPUs face a stark engineering mismatch. Raw computational power has scaled significantly faster than the memory bandwidth required to feed the processor. Inside the GPU, data is stored in high-bandwidth memory, or HBM, but the actual matrix mathematics happens at the tensor cores, which pull data from a smaller, high-speed cache called SRAM. The tensor cores execute calculations almost instantly. They then sit idle, waiting for the next massive block of weights to cross the physical channel from memory. Because language models generate text one token at a time, the GPU must reload static weights across that channel for every single word it writes. In this architecture, maximizing inference speed is less about compute power and more about data movement. To generate a new token, the model evaluates its current prompt alongside the entire history of the ongoing conversation. Recalculating the mathematical projections for thousands of previous words on every forward pass would consume a prohibitive amount of computation. Instead, inference engines save this historical context directly in VRAM. This is the KV cache. It stores the previously calculated key and value vectors, so the model only performs the math for the newest token. The memory footprint of this cache is substantial. It scales by multiplying the model's layers, attention heads, dimension size, and data precision. If a user processes a 128,000 token document with Llama 3 70B, the KV cache alone demands 40 gigabytes of memory. This dynamic cache expands with every word, competing with the static model weights for the remaining space in VRAM. Without precise management of this growing cache, a single server can only support 2 or 3 concurrent users before the memory is completely saturated. Traditional serving frameworks waste memory by allocating space upfront based on a request's maximum potential length, rather than the text actually generated. Reserving a contiguous 2048 token block for a short question locks away up to 80% of that capacity, leaving it wasted. The vLLM engine addresses with PagedAttention, adapting operating system virtual memory paging to the GPU. Large memory reservations are broken into small, fixed-size blocks. A dynamic table maps these scattered pages, allowing multiple user requests to share a single physical memory pool safely. Allocation shifts from maximum potential to on-demand. The system only assigns a new physical block when a token is actually written. Reclaiming that wasted memory allows the same hardware to support up to 18 parallel users instead of 2. Static batching creates another bottleneck. If one request in a batch is a single sentence and another is a full paragraph, the short request sits idle until the long one finishes. Continuous batching solves this by moving the scheduling logic to the individual token level. The scheduler evaluates the active queue during every forward pass. The moment a request finishes, its memory slot is freed, and a waiting request is immediately injected into the active stream. This ensures that compute cycles and memory bandwidth are kept near 100% utilization, removing the traditional throughput ceiling. With the serving engine optimized, engineers can reduce the physical footprint of the weights through post-training quantization. Precision reduction is often met with concern that aggressive compression will erode the model's reasoning capabilities. A common configuration is W4A16. This compresses static weights to 4-bit integers while maintaining the dynamic activations at 16-bit precision. The 4-bit weights travel out of HBM significantly faster. Once they reach the high-speed SRAM, they are expanded back to 16 bits for the final calculation. Halving the volume of data crossing the memory bus directly translates to a faster time to first token. Alternatively, weight and activation quantization, or W88, targets the execution itself. In W88, both the weights and inputs are 8 bits. They do not expand in the SRAM. Instead, the tensor cores execute the matrix math natively at lower precision. Removing the expansion overhead allows the processor to handle a significantly higher volume of tokens per second. By using calibrated datasets to protect the small percentage of outlier parameters, quantization becomes a precise tool to bypass bandwidth limits without sacrificing output quality. Optimization choices must be validated against service-level objectives tailored to the business use case. This requires measuring two vectors: performance under load using guide LLM, and logic retention using an evaluation harness like LM_eval. This curve plots throughput against latency. Guide LLM simulates high-traffic scenarios to identify exactly where latency spikes past the acceptable threshold. Success is measured at the P99 percentile. A deployment that is fast on average still fails if 1 in every 100 users experiences an unacceptable delay. Concurrent load testing is the only empirical way to prove an infrastructure deployment will maintain performance under corporate traffic. High-efficiency serving relies on 3 compounding stages: compressing the weights, serving with virtual memory paging, and measuring the bounds. On a model like Qwen 3.06b, the hardware gains are measurable. This configuration yields a 42% footprint reduction while maintaining 95.3% of the original model's accuracy on the HeliSwag benchmark. First, quantization addresses the data movement bottleneck, while PagedAttention manages the expanding memory demands of the KV cache. By layering these engineering techniques, teams can run state-of-the-art frontier models up to 10 times cheaper while preserving their intelligence.